Hello class, today we are going to be going through our first topic of the week, and that is comparing linear, exponential, and quadratic functions. We're going to do so by looking at a different variety of ways that we can display these functions. One is by looking at a graph, one is by looking at an equation, and then we can also determine different functions based on like a scatter plot or even a table of points. So we're going to look at all of these different varieties and try to be able to distinguish between which of these functions it currently is. I'm going to just summarize the first video that you guys should have already seen given to you by the county. I'm going to summarize it on this just blank piece of computer paper. I've jotted some notes down, and then we're going to use this information to help us answer and go through our first classwork assignment of the week. Okay, so first off, let's start dealing with our linear function. So I don't have a ruler with me, so please don't judge me too harshly. But a linear function, we know, is something that is either increasing or decreasing at a constant rate. A linear function makes a line. Usually we're used to seeing the actual function in like y equals mx plus b form. That's that slope-intercept form. So I'm going to jot this down. My first function is a linear function, and I'm just going to do that slope-intercept form. We know that there's a lot of different ways that I can write a linear equation, but that is one that is relatively common with you guys. Okay, so now it asks us a couple of questions, and these questions down here are going to be able to help us differentiate between our three functions that we're going to discuss today. So if you remember, domain is always how far my graph is going to go to the right and to the left. We always go least to greatest, so we read it just like a book. We read it going from left to right. If I notice here, my graph has arrows. Those arrows are signifying that function doesn't just magically stop there. Those arrows are representing that it's going to keep going in those directions forever. So if you can picture this arrow is pointing down towards the left. I don't care that it's going down. I care that it's going to the left. Domain is left and right. It's going to continue going to the left forever. So basically what that means is it's going to be approaching that negative infinity. All right, it's kind of like that sideways 8, right? And then if I'm looking towards my right, the same thing is happening here. I have an arrow. It's going to keep creeping to this right forever and ever and ever, never stops. So it's going towards positive infinity. All right, so my domain, if you remember, this is called all real numbers. It goes from negative infinity to positive infinity. All right, the range is now looking at my y values. I care about the height of my function. Right? I no longer care about left and right. I don't care about the width. The range is talking strictly about the height. So once again, I run into an arrow. This arrow means that it's going to keep going down forever and ever and ever. So it is going to be approaching that negative infinity. And if you remember why negative infinity gets a parenthesis, it's because we don't know what that number was. Like we don't know what infinity is, right? Nobody's been able to calculate that. All right, and then now I'm going up. I'm going to figure out how high this is going to go. I run into another arrow. It is going to keep going up forever. So it's going towards positive infinity. All right, every single linear function has a domain of all real numbers and a range of all real numbers. Every single one of them can never be differentiated from that. It's always that. All right, a couple of graphical characteristics. We know that a linear function creates a line. Right, that's like the easiest one to tell. A quadratic and exponential, they're kind of curves. They don't go up at a constant rate like this. So one of the graph characteristics is it does create a line. A linear function is a line. All right, table characteristic, this is the one that we want to pay a little bit closer attention to. I'm just going to come down here and jot down a little XY table. And I hope I'm giving myself enough space. All right, so I'm just going to make some numbers up. Let's start at 0. Let's go up 1, 2, 3, 4. And then my table here, let's make my life as difficult as possible. So I'm going to pick some negative numbers. All right, and then we're going to go here, here, and here. All right, so right off the bat, I could take these points and I could plot them on a scatter plot. And then I could connect them to see what kind of function it looks like. Does it look like a line? Or if I have really crazy, outrageously large numbers, like this was 0 and like negative 3 billion, like I don't want to have to graph that. So there's got to be an easier way. All right, so looking at the table, I'm going to first look at my x values and make sure they're just going up at a normal rate. I don't want this to go like 0, 1, 7, 15, like 0, that's going up by 1, going up by 1, going up by 1, going up by 1. So I'm good there. All right, so once I have that established, I want to just look at my y values now. I'm trying to see if I can find a pattern. All right, we've already learned this at the very beginning of the year, but linear functions have constant first differences. That means when I find the distance between these two numbers, if this is a linear function table, it's going to be the same distance between all of these numbers. So if I'm sitting at a -3, I have to go up 3 units to get to 0. From 0 to 3, I have to go up 3 units. From 3 to 6, I have to go up 3 units. And then from 6 to 9, I have to go up 3 units. All right, so since all of these numbers are the same, I know it's a linear function. So under our table characteristics, we know that the first difference, let's see if I can make this, first difference is constant. That just means that when I'm finding the distance between my y values, they're all the same. First difference is constant. Sorry, a little sloppy there. Not used to writing without my erasable pens. Okay, so that is all the characteristics about a linear function. So now let's move on to our second function in no particular order. Let's go through and do a quadratic. Let's just do like the parent function of the quadratic. Looks something like that. All right, we are dealing with the quadratic function, a bunch of different ways that we can write this. Let's write this in standard form. So that's like the ax squared plus bx plus c. All right, domain, once again, going from left to right. So I want to always look at these arrows. All right, remember, in a quadratic, these tails of the parabola never go vertically up. If I wanted to exaggerate this a little bit, it's going to keep going to that left forever. It's going to keep going to the right forever. So just like a linear function, the domain, let me get the correct color here, the domain of a quadratic will always be -infinity to +infinity every single time. It will never be anything else. The range, however, is a little bit different. All right, if you remember, the range is how low the graph goes to how high it goes. This one, it has that turning point, that vertex. So this parabola, this quadratic function, doesn't keep going down forever like our linear function did. It actually reaches a minimum. Remember, the vertex is also known as the minimum or the maximum. In this picture, it's known as a minimum. So if my picture was drawn perfectly, I would see that this comes down to 0, right? A height, a y value of 0, and then it goes back up. Right, so my lowest number that this reaches is a 0, and that's when the numbers get brackets. If it goes directly through a number, it gets a bracket. All right, and then now I care about how high this graph is going to go. All right, this graph looks like I have my arrows going up, so it's going to keep going up forever, so I know it's approaching that positive infinity, right? So this is interval notation. Domain is all real numbers, goes to the left and to the right forever. My range, the lowest point is a 0. Remember, I'm looking at my y-axis, and my highest value is infinity. All right, a graph characteristics, it is that U-shaped, so I'm going to write that U shape, which all of you guys should know that is called a parabola. It is a parabola shape. It is that U shape. All right, table characteristics. This one starts getting a little bit tricky, so make sure you guys focus on this part. Okay, I'm going to draw myself a little XY table. Oh, nice little squeaky sound. Sorry about that. 0, 1, 2, 3, 4, and 5. All right, 1, let's go 6, 17, 34, 57, and 86. Okay, I did look this up beforehand. I'm not super genius, and I didn't just make these numbers up on the fly. Okay, so just like a linear function, because I don't know what this is right now. I mean, I know it's not linear. This goes up by 5, and then this goes up by 11. So I know it's not the same number going up. So right off the bat, I know it's not a linear function. One little trick that you might always want to look at is if you look at these numbers and they start going up, but then they start going down again, or vice versa, that's a pretty good indication that it might be a quadratic function, because if you look, our shape goes down, but then comes back up. So let's first look at our y values. It looks like I'm increasing, still increasing. So I don't actually see a vertex here. So I can't just say, oh, it's a quadratic, because I don't see it go up and then go back down. So just like my linear function over here, I want to check these differences. All right, so between 1 and 6, that is 5. 6 and 17, that is 11. I want to make sure I don't make a mistake here. 17 and 34. If you are super sure that you don't want to make a mistake, grab a calculator. What we're doing is we're just taking, my calculator seems to be dead. Oh, yeah, she's dead. All right, we're just taking the second number and we're subtracting the first number. So I did 6 minus 1 to get 5, 17 minus 6 to get 11, 34 minus 17, and that's going to give me a 17. All right, 57 minus 34 gives me 23. And then lastly, 86 minus 57. That's why it's called differences, because we're subtracting. 86 minus 57 is 29. Whew, that's some stressful math when I'm being recorded here. Okay, so right off the bat, I know it's not linear. These numbers are not the same. So the first differences are not constant. Let's keep going and let's check to see if the second differences are constant. So when I do 11 minus 5, I get 6. 17 minus 11, and I get 6. 23 minus 17, 6, and 29 minus 23 is also 6. So if you notice, when I'm dealing with a quadratic table, the second differences were constant. All right, so second difference is constant. All right, excuse me, a little tidbit of knowledge here. The first difference was constant in a linear function because isn't the exponent of this x technically a 1? Right, I have 1x there. In a quadratic, I have an x squared. The second difference is constant. So this isn't important for this week's lesson, but if I had a cubic function, let me just jot this down over here. Not to confuse you, but just a little tip there. A cubic function looks like this, y equals x, excuse me, x cubed. Since my exponent is a 3 here, if I did this table, I'd have to go through one more time to find out that the third difference was constant, and therefore it'd be a cubic function. Okay, last function is my exponential function. We've already talked about, excuse me, we already talked about this in our earlier weeks there. Excuse me, I'm like choking on like a bagel or something. Sorry about that. Exponential function is either growth or decay. It grows very, very, very quickly, or it decays very, very quickly. So it could also start up very tall and then come down like this, but it looks something very, very similar to this. So let me get a different color here. Let's go with purple. So this is an exponential function. And like I said, we have exponential growth or decay. This picture here is a growth. As you read it from left to right, like a book, it is getting larger. All right, so this looks something like this, a times b to the power of x. We'll get into the actual form of the equations probably a little bit later. Let's check our domain. Let's look at these arrows here. Hopefully you guys agree with me that this is going to continue going to the left forever. And this right here never plateaus. It never goes perfectly vertically up. It's going to keep going in this direction. So it's going to keep going to the right forever. So something you guys should never get wrong is if I say, what is the domain of a linear, quadratic, or exponential function? The answer is always going to be all real numbers from negative infinity to positive infinity. All right, the range is a little bit tricky, little bit tricky here. So if you guys remember earlier on, we talked about something called an asymptote. So that is A-S-Y-M-P-T-O-T-E, an asymptote. Rolls off the tongue nicely there. What that means is this exponential function will never dip below this line. So it doesn't plateau, but it just keeps getting infinitely closer to this line without ever actually touching it. So if you think about this, like if we're talking about like bacteria and it is growing, the bacteria was never at 0. There had to be something there for it to start growing. Or like if you're talking about like a savings account, like yes, you might lose money in a savings account, like if you invested in the wrong things, but you will never ever have like $0. You might have a couple of pennies in there, but it's never actually going to approach 0. So going off my height, it gets really, really close to 0, but it doesn't touch it, so it gets a parenthesis. All right, and then as I go up, it's going to keep going up very, 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 very quickly. It goes towards infinity. So very similar to that of a quadratic function, except for it never actually reaches 0. In the quadratic function, it actually touches 0. All right, all right, graph characteristics. I'm just going to say it either grows or decays quickly. Right? It starts super, super slow. It's barely getting taller, and then all of a sudden it's just like, boom, it goes up, right? All right, table characteristics. I'm gonna try to make this up on the fly here. So we have our x and y. Let's go 0, 1, 2, 3, 4. And then let's go with like, let's do smaller numbers here so I can do it on my head. Let's do like a 1, 2, 4, 8, and 16. All right, so I always look to see if it's linear first, just because that's the easiest. I can add pretty quickly in my head. From 1 to 2, it's +1. 2 to 4 is +2. So those aren't the same numbers like it was over here, so I know it's not linear. All right, then I might check to see if it's quadratic. The distance here is a 1, the distance here is a 2, which makes that a 1. So like it's not going to work because these numbers are getting up pretty quickly. I can also tell that in my y column, it's just strictly increasing. I don't see that vertex. My numbers don't go up and then down. So I know it's definitely not a quadratic in that regards. The way that we check to see if it is an exponential function is by looking at the ratio. So what I'm going to do is I'm going to take 2 and divide it by 1. Right? 2 divided by 1 is a 2. Right? Then I'm going to take 4 and divide it by 2, and that gives me a 2. I'm going to take 8 and divide it by 4, and that gives me a 2. And then lastly, 16 divided by 8, and that gives me a 2. So I'm not doing differences anymore. I'm not subtracting. I'm actually dividing, right? So table characteristic about an exponential function, it has a common ratio. And maybe in parentheses, you might want to say you have to divide to find that common ratio. All right, guys, so you should have gotten all of this out of the county video for topic 1. I'm now going to transition over to the classwork example. That'll be in the second video.